Hello and greetings everyone. My name is Abdurrahman Mohammed Mahmoud Nasif and I'll be presenting my final year project entitled Complex Phase Diagram of Phenol and PAH in Exhaust from Diesel Engine. As an introduction, a diesel engine is an internal combustion engine that consists of cylinder and piston, which is operated with a crankshaft whereby it converts chemical energy stored in the fuel into mechanical energy, which is utilized to power the vehicle. To convert the chemical energy of the fuel into useful mechanical energy, a diesel engine is operated by a cycle of 4 stages of 4-stroke, which are intake, compression, power, and exhaust. However, the main disadvantage or the main drawback of the diesel engine is its nitrogen oxide emission. When compared to a gasoline engine, it produces more NOx emission. This is because the diesel engine operates at a higher temperature and pressure than the gasoline engine. These conditions favor the production of NOx gases. NOx is formed in the combustion chamber of the engine at high temperature, whereby nitrogen bound in the fuel reacts with excess oxygen in the air intake. To mitigate the problem of NOx emission, an emission control technology known as exhaust gas recirculation or EGR are currently being equipped with diesel engines. The main function of an EGR is to decrease NOx production produced from diesel engine. So how does an EGR work? As you can see in the figure 2, a fraction of the exhaust gas is recirculated back into the intake manifold where it mixes with the inflowing air intake. So by recirculating the exhaust gas into the intake, some of the oxygen required for the combustion is replaced by exhaust gas, which lowers or results in a lower combustion temperature, hence reducing NOx emission. However, there is a major disadvantage of an EGR system. The formation of particulate matter known as soot in the exhaust pipe increases when EGR is applied. As I mentioned before, the EGR lowers combustion temperature, which results and reduces the amount of nitrogen oxide produced, but it increases the likelihood of soot formation in the exhaust. As you can see in the figure, the reduction of nitrogen oxide simultaneously promotes the soot deposit in the exhaust. If left unchecked, the accumulation of the soot significantly hinders the performance and durability of the engine. And lastly, microscopically, the soot is found to have some sticky compound. One of the sticky compound that is found in the soot is phenol resin. According to Fukuroka, traces of sticky phenol resin were found in the soot from the exhaust, and it is believed to be synthesized by the reaction of phenol with formaldehyde at 80 to 150 degrees Celsius in the diesel engine, and this reaction is shown here in the slide. The other component that is found in the soot is polycyclic aromatic hydrocarbon, or known as PAH. Here are some examples of PAH, and they are naphthalene, phenanthrene, anthracene, and pyrene. So basically the soot mainly consists of two compounds, and they are the sticky phenol resin and PAH. Next, for the problem statement of this project. So at present, EGR systems are efficiently reducing NOx emission. However, it results in increased formation of soot in the exhaust, which eventually over time results in the blockage of the exhaust pipe. This accumulation of soot significantly hinders the performance and durability of the engine. This soot produced is a sticky substance that contains mainly phenol and PAH. Some researchers pointed out that the effect of PAH to promote condensation and coagulation of phenol, but the mechanism have not been clear yet. Technical insight regarding the mechanism and the condition at which the soot is formed in the exhaust of the diesel engine will be identified using phase equilibrium equation. Next, the research objectives for the studies are to calculate the vapor-liquid equilibrium and solid-liquid equilibrium for the binary mixture of phenol and pyrene, to construct the phase diagram for the binary mixture of phenol and pyrene, and the last objective is to identify the mechanism of the soot formation in the exhaust. As for the methodology, the method used will be solely based on manual calculation using phase equilibrium equations. Next, phenol and pyrene were chosen as the two components of the binary mixture. Next, the phase equilibrium is evaluated using solution model. And before undergoing the calculation, a few assumptions were made in order to assist with the calculation, and they are: the first assumption is the binary mixture of phenol and pyrene is assumed to be ideal gas and ideal solution. Next, a simple eutectic binary for solid liquid equilibrium. Next, there will be no pressure dependence for the melting point of phenol and pyrene. And the last assumption is that the total pressure is constant throughout the exhaust at 101.35 kilopascal, or in other words, atmospheric pressure. Firstly, the solid liquid equilibrium for the binary system of phenol and pyrene was calculated using the two following equation, which is given by x1, x2, which is the mole fraction in liquid phase, Tm1 and Tm2, which is the melting temperature of phenol and pyrene respectively, and H1 and H2 is the heat of formation. Since we assume that the binary system of phenol and pyrene to be a simple eutectic binary and an ideal solution, the activity of the mixture is given by the mole fraction in liquid phase, which is x1 and x2. Furthermore, as you can see in the figure here, the temperature at point B and A represents the melting temperature of pure solid 1 and solid 2, which in our case is phenol and pyrene respectively. The curve BE represents the liquid curve on which pure solid 1 is in equilibrium with the liquid mixture and is given by the first equation. Similarly, the curve AE is the liquid is curve in which the pure solid 2 is in equilibrium with the liquid mixture, and it is given by the second equation. Furthermore, the curve AE and BE intersects at a point which is known as the eutectic point. At the eutectic point, the liquid mixture is in equilibrium with both solid 1 and solid 2. Furthermore, the melting temperature and the heat of formation is given by the pure compound, which in our case is phenol and pyrene, since we assume the binary mixture is an ideal solution, and the value of the melting temperature and the heat formation is given in table 1. Next, for the vapor-liquid equilibrium calculation, the mixture is assumed to be an ideal solution and an ideal gas. Since we are using the solution model condition, which is only applicable for the liquid phase, hence ideal gas is used to extend to gas phase. So at the equilibrium condition, the fugacity of the liquid phase and the vapor phase are the same. Hence, the vapor-liquid equilibrium for the binary mixture is calculated using the following equation. The equation is given by P1, which is the partial pressure, P1 naught, which is the saturated vapor pressure, X1, which is the mole fraction in liquid phase, and Y1, the mole fraction in vapor phase. Furthermore, the saturated vapor phase is calculated using this following equation, whereby the regression coefficient or the value of A, B, C, D, and E is given in table 2. Next, I'll be explaining about the result and discussion of the project. Based on the calculation of VLE and SLE, the mixture of phenol and pyrene at pressure of 101.35 kilopascal, the phase diagram was constructed as you can see in the slides. According to the phase diagram, the temperature ranged from 0 to 680 Kelvin. This region here is represented by the vapor-liquid equilibrium, while this region is represented by the solid-liquid equilibrium. The region above the dew point curve represents the binary mixture is in equilibrium at vapor phase. Next is the region between the dew point curve and the bubble point curve, and it represents the binary mixture is in equilibrium with both vapor and liquid phase. Furthermore, the liquid binary mixture is in equilibrium with the solid pyrene at this region. Similarly, in this region, the small region here, the liquid binary is in equilibrium with the solid phenol. Lastly, the eutectic point was evaluated at Xe equal to 0.925. So below the eutectic point, the mixture is in equilibrium, exists in solid phase. It's in equilibrium in solid phase. Next, let's see how does the phase diagram can help to understand the formation of the soot in the exhaust pipe. We set the condition at X1 equal to 0.1, or in other words, 10% phenol. So firstly, at the temperature of 680 Kelvin, after the exhaust gas is expelled into the exhaust pipe, the mixture is completely in vapor phase. As the temperature completely drops to 553 Kelvin, small amount of phenol begins to promote the condensation of the mixture. This means that the mixture begins to convert into liquid phase. This is because the bubble point rapidly decreases. Next, as the temperature drops to 500 Kelvin, at this stage, the mixture is completely condenses into liquid phase. Next, as the temperature is at 415 Kelvin, at this stage, the liquid mixture begins to solidify and the soot is deposited at the exhaust pipe. Lastly, at 308 Kelvin, the mixture completely solidifies and the soot is formed in the exhaust pipe. As a conclusion, the phase diagram provided a technical insight regarding the mechanism and the condition at which the soot is formed in the exhaust of the diesel engine. The phase diagram suggested that the condensation by phenol caused a soot deposit in the EGR system at 415 to 553 Kelvin. So therefore, a new device at the specified temperature would be required to avoid mechanical trouble caused by soot deposit. And thank you for listening.